Welcome back to the deep dive.
Yeah.
Just take a second and think about everything digital around you right now. Every single thing. Streaming a show, getting that notification your package just arrived.
Yeah, all that real-time stuff.
It's all powered by this kind of invisible conversation happening between, computers all over the place, distributed systems talking.
Exactly. It's this hidden infrastructure, and right at the core of that, you've got these two big players,
Yeah.
REST APIs and webhooks.
Right. They're basically setting the rules for how these systems talk and swap data.
But the thing is, as we rely more and more on everything being connected, designing these things right for scale, for maintenance, and especially for security, that challenge just gets bigger and bigger.
Yeah, it really does. And that's exactly why we're here today. We've gone through, well, a lot of technical docs, standards, even detailed reports, but when things went wrong.
A mountain of reading.
Pretty much. And our mission for you today is simple. We want to give you that shortcut to really getting it. Not just the what they are part, but how to actually master the design principles behind them and critically figure out when to use which one, making that strategic call.
Yeah, that's key. So we're going to start with the basics, the sort of foundational rules that let REST work globally. Then we'll really dig into that pull versus push decision.
Okay.
And then this is crucial. We're going to look hard at the vulnerabilities. Think like the OWASP API security risks.
The scary stuff.
Exactly. But illustrated with real-world examples, actual breaches, showing how these little design mistakes can, well, blow up spectacularly.
Okay. So if you're ready to really understand the plumbing that powers, well, almost everything digital now, let's get into it. Tag 2, the foundational architecture of REST. All right, let's kick things off with REST. Representational state transfer, you hear it constantly in software development.
Yeah, all the time.
But it often gets kind of misfiled, doesn't it? People think it's a protocol.
They do, and that's the first big clarification from all our sources. REST is definitely not a protocol. It's an architectural style.
Okay, architectural style. Why is that distinction so important?
Well, it means it's a set of guiding principles, constraints, really. Came out of Roy Fielding's PhD work, actually. And the reason it took off, why it's basically the standard now. It's simple, it works beautifully in distributed systems, and it just fits perfectly with HTTP, the engine of the web.
Got it. So let's talk about those constraints, the rules that actually give REST its power, its scalability. First up, client-server separation.
Right. This one's fundamental. It demands a clean break, a total separation of concerns. The server, its only job is managing data, providing resources.
Okay.
The client, that's all about the presentation, the user interface, making the requests. They shouldn't really know much about each other's inner workings.
And the benefit there is?
Decoupling, massive decoupling. It means your web team, your mobile app team, maybe even an IoT team, they can all build and update their stuff independently, talking to the same back-end API.
So one API can serve totally different front ends without the server needing to change for each one.
Precisely. That's huge for scaling things out horizontally. You can add more server power without messing with the clients.
Makes sense. Okay, principle number 2, and you said this one's maybe the most critical. Statelessness.
Yeah, statelessness. This is the one that tends to confuse people the most, especially when you're building complex apps that obviously have state.
Right. Like a shopping cart or being logged in. That feels very stateful. How does REST handle that if it's stateless? Define it for us.
Okay, so statelessness means every single request from the client has to contain all the information the server needs to understand and process it. Authentication tokens, what resource you want, any necessary context. It all has to be right there in the request.
So the server doesn't remember anything about you from one request to the next.
Exactly. It stores absolutely zero client-specific session context between requests. Each request is treated in complete isolation.
Okay, but back to my shopping cart example. That state has to live somewhere. Where does it go if not on the server?
Right. And that's the clever part.
Yeah.
It's delegation. The API itself is stateless, but the application state isn't lost. It's just managed somewhere else.
Ah, okay. So you push the state management. Where?
Usually two places. Either back to the client itself, maybe using things like JSON Web Tokens, JWTs, and the request header, which contain state info.
Like user ID, roles, that kind of thing.
Exactly. Or you delegate it to other dedicated stateful systems like your main database or maybe a distributed cache like Redis. The API server stays clean and stateless.
Okay, let me push back slightly, though. If every single request needs a security token, like a JWT, and the server has to validate that signature every time, doesn't that just shift the bottleneck? Instead of memory for sessions, you've got constant crypto processing.
That's a really good question, and it gets right to the trade-offs. But the overhead of validating a JWT signature, especially with modern libraries and async keys, is generally much lower and scales better than trying to manage session state across, say, hundreds or thousands of distributed server instances.
How so?
Well, with JWTs, often using public-private keys, any server instance can validate the signature without needing to phone home to some central session database. It just checks the math.
Ah, I see. So any server can handle any request because the request itself proves who the user is.
Exactly. That's the magic for scaling and resilience. If one server dies, the client just sends the same request with the same token to another server. No lost session, no disruption.
Okay, that clicks. Simplify the server, maximize resilience. Got it. Let's move on to the third key constraint, the uniform interface.
Right, the uniform interface. This is all about making APIs predictable, easy to understand, and interoperable. It's like establishing a common language. It has four main parts.
Okay, what are they?
First, resource identification. Everything you want to interact with a user, a product, an order needs a stable, unique identifier, a URI, like products 45. Simple and clear.
Makes sense. Number 2.
Second, resource manipulation via representations. You don't send commands like update user. Instead, you send a representation of the resource, usually JSON or XML, showing the state you want it to be in.
So you send the data, not instructions.
Pretty much.
Ah.
Third, self-descriptive messages. The request itself has to carry enough info for the server to understand it. This is where HTTP headers are vital. Content type tells the server it's JSON, accept tells it what format you want back, caching headers, etc.
Okay. And the fourth part?
Fourth, and really important, is using standardized HTTP methods. Get, post, put, delete, patch. We stick to these standard verbs defined by HTTP instead of making up our own, like get user details or create new order.
And using those standard methods has big benefits, right? Especially for things like security gateways.
Absolutely. Because they're standard, tools like API gateways or firewalls can understand the intent of a request just by looking at the method and apply consistent security rules, like maybe allowing getTs broadly but heavily restricting deletes.
All right, so we've got the core principles: client-server separation, statelessness, uniform interface. Now, how do we actually build APIs that follow these rules and scale well in the real world? Let's get into the design playbook, maybe starting with resource naming.
Yeah, good API design is readable, it's predictable, and the best practice here is really clear. Use nouns, not verbs, for your resource paths, and typically plural nouns for collections.
So users, not get all users or fetch user?
Exactly. It reflects that REST is about interacting with resources, not calling remote functions. You're getting users, posting to users, getting users 1, 2, 3.
Okay. And how do you show relationships between resources? Like if a user has blog posts.
You use hierarchy, nesting. It makes the structure intuitive. So if user 123 has posts, the path would logically be users 123 posts.
Right, like a folder structure.
Kind of, yeah. And if you wanted a specific post, say post 45 belonging to user 123, you'd just continue nesting. Users 123 posts 45.
That path itself basically tells you what you're dealing with. It's like self-documentation.
It really is. It makes the API much easier for developers to pick up and use correctly.
Okay, next point. Making sure we use those HTTP methods correctly. It's not just using get, post, put, delete, but using them for the right operation.
Absolutely crucial for predictability. You need to map the standard CRU'd operations, create, read, update, delete directly onto the right HTTP verbs. And there are nuances, especially with updates.
Let's break that down.
Okay. Create maps to post. You post to a collection URI, like users, to create a new user. The server usually responds with the new resources URI.
Got it. Read.
Read is get safe. Should never change anything on the server, just retrieve data, and it should be idempotent, meaning calling get2 multiple times has the same effect as calling it once.
Okay, update gets tricky, right?
Yeah.
TG versus PLCH.
Yes. This distinction is important. UPdate using PT is for full replacement. If you put to users 123, the server should replace the entire user 123 resource with the data you sent in the request body.
Meaning, if I forget to include the user's email in my PUT request,
their email might get wiped out or set to null in the database, depending on the implementation. PUT replaces the whole thing.
ouch. Okay, so PAT-CH is for?
PAT-CH is for partial updates. If you only want to change the user's phone number, you send a PAT-CH request with just the phone number field. The server applies only that change, leaving everything else untouched.
Much safer for targeted updates.
Definitely. And finally, delete maps to delete. Pretty straightforward, removes the resource specified by the URI.
Using these methods correctly really aligns with the whole REST philosophy, doesn't it?
Yeah.
Predictable actions on resources.
Exactly. And misusing them, like using get to delete something, is a major anti-pattern and can cause all sorts of problems, including security issues.
Okay, another part of this playbook has to be how we handle things when they don't go right. Error handling.
Yes. A predictable API needs predictable error responses, too. That means using the standard HTTP status codes correctly. Don't just throw a generic 500 internal server error for everything.
Right, so give us the rundown.
Success is usually 200. Okay, or maybe 201 created if you made something new. Client errors, problems with the request itself, are the 400 series.
Right.
400 bad requests for malformed input, like invalid JSON. 401 unauthorized if the user isn't logged in or provided bad credentials. 403, forbidden, this is key, means the user is logged in but doesn't have permission to access this specific resource or perform this action. And 404, not found, means the resource URI doesn't exist.
Using 401 versus 403 correctly is super important for security diagnostics.
Crucial. And using the right 4IX code tells the client developer exactly what they did wrong so they can fix it instead of just guessing.
Okay, last piece of the design playbook. Versioning. APIs change, evolve. How do we manage that without breaking things for existing users?
Yeah, versioning is essential because APIs aren't static. You need a way to introduce breaking changes that aren't backward compatible without disrupting clients using the older version.
What's the common way to do it?
The most common and arguably clearest way is URI versioning. You stick the version number right in the path, like V1 users becomes V2 users. Figure 4 in our source material actually shows this transition. It's explicit. Everyone knows what version they're hitting.
Well, there are downsides to putting it in the URI.
Some purists argue it pollutes the idea of a stable resource identifier. The resource itself hasn't changed, just its representation or behavior, so alternatives exist.
Like what?
You could use a query parameter like users.version2, or you could use a custom HTTP header like acceptVersion.v2. Header-based versioning is maybe cleaner architecturally, but it's less visible, less explicit than URI versioning.
So which one should you choose?
There's no single right answer, depends on the context. The key rule, regardless of method, is only introduce a new version for actual breaking changes. For minor additive changes that don't break existing clients, you should aim for backward compatibility within the same version. Maybe just documenting the new features, don't over-version.
Okay, so REST is fundamentally pull-based, right? The client asks, server responds.
Client initiates.
But sometimes you need the opposite. You need the server to tell you something happened immediately without you having to constantly ask. That's where webhooks come in.
Exactly. Webhooks flip the script. It's the don't call us, we'll call you model for APIs. It's a push mechanism.
So instead of me pulling an API endpoint every 5 seconds asking, is my order shipped yet? Is it shipped yet?
Right, which is incredibly inefficient.
The shipping system just tells my system, hey, order 123 just shipped the moment it happens.
Precisely. That's the core idea. It's event-driven. An event occurs on the server side, an order shipped, a payment processed, a user signed up. And the server proactively sends a notification, an HTTP request, to a pre-registered URL on the client side.
You mentioned polling being inefficient. Our sources really hammer on this polling predicament, don't they?
They do, because polling, especially for infrequent events, is just wasteful. Think about it. You make potentially hundreds or thousands of API calls that return nothing new. Nope, still not shipped. Nope, nope.
Yeah, I've been there. Burns CPU on both ends. Uses bandwidth, adds latency because you only find out after your polling interval.
Exactly. Webhooks eliminate all that waste. You only get a call when there's actually something to report. It's far more resource-friendly and provides much lower latency for event notifications.
Okay, let's walk through the life cycle. Say, I run an e-commerce store, and I want my inventory system, a separate service, to know immediately when a product goes out of stock. How does that webhooks setup work?
Okay, step 1 is registration. Your inventory system, the client, the listener, needs to tell your e-commerce platform, the provider, the source of the event, where to send notifications. So the inventory system provides a publicly accessible URL endpoint that it controls.
My webhook receiver.
Exactly. And it usually specifies which event it cares about, like product.out of stock. Step 2 is the trigger. A customer buys the last widget. Boom, the product.out of stock event fires inside the e-commerce platform.
Okay, then what?
Step 3, notification. The e-commerce platform immediately constructs an HTTP request, usually a POST request. Inside the body, typically as JSON. It puts details about the event. Which product, timestamp, maybe the remaining quantity, 0.
Edit.
And then it sends that post request asynchronously to the URL your inventory system registered back in step 1. The inventory system receives it and updates its stock levels.
So that notification is just an HTTP request. This brings up a point of confusion I've seen. Is a webhook just another type of REST API? How are they actually different?
That's a common misconception. A webhook uses HTTP, just like REST APIs do, but it's better to think of a webhook endpoint as a specific single-purpose API designed for receiving event notifications. It's kind of a subset serving one function.
Okay, so the core difference isn't the technology HTTP, but the flow, the initiation.
Precisely. REST is pull-based. The client asks, give me data. It's typically synchronous, you wait for the response. A webhook is push-based. The server says, hey, something happened. It initiates the contact. And it's usually asynchronous. The server sends a notification and doesn't necessarily wait for a complex response.
Right. Different communication patterns.
Yeah.
So let's get strategic. When does it make sense to stick with REST, pulling, and when are webhooks pushing clearly the better choice?
You'd lean towards REST pull when the client needs data on its own schedule, on demand, or when you need to perform complex queries, filter data in specific ways, or fetch historical information.
Like a dashboard pulling sales figures for the last quarter.
Exactly. Or a mobile app fetching the user's profile when they navigate to the settings screen. The client is in control, asking for what it needs when it needs it.
Okay, and the prime time for webhooks. Push.
Webhooks shine when you need real-time updates. When latency matters and you want to react immediately to an event happening elsewhere, avoiding polling is the other huge driver. Think about notifications like Slack or Trello. A new message arrives, a card is moved, you get notified instantly. E-commerce order confirmations, payment gateway alerts saying payment successful, triggering downstream workflows like shipping. Anything where you want System A to kick off an action in System B the moment something happens in A. That's webhook territory. #tag V. Hybrid architectures and performance optimization.
So it sounds like it's not always an either situation. Our sources suggest the most robust systems often use both REST and webhooks together, right? A hybrid approach.
Absolutely. The most resilient, sophisticated architectures often leverage the strengths of both models in a complementary way. It's not REST versus webhooks, but REST and webhooks.
How does that hybrid pattern typically work?
The common pattern is to use the webhook as a lightweight signal. It's like a quick tap on the shoulder saying, hey, event X just happened. Here's the event ID. Very minimal data.
Just a notification, like a text alert telling you something happened.
Exactly. Then, the system that received the webhook notification is responsible for making a follow-up REST API callback to the source system using that event ID to fetch the full, detailed, canonical data about the event.
Ah, okay. So the webhook says, order 123 updated. Then my system calls get orders 123 on the REST API to get the actual order details.
Precisely.
But why the two steps? Why not just cram all the order details into the webhook payload itself? Seems simpler.
Two main reasons, resilience and security. First, resilience. Webhooks, especially over the public internet, aren't guaranteed delivery. Messages can get lost, duplicated, or arrive out of order sometimes. By sending only a minimal signal, you reduce the impact if a webhook fails. The real data transfer happens via the robust, often idempotent REST call.
So if the webhook notification gets lost, you haven't lost the actual order data, just the heads up.
Right. And second, security. You generally don't want to send sensitive information, personal details, financial data directly in a webhook payload. It's better practice to keep that data secured behind your properly authenticated REST API endpoints. The webhook is just a trigger. The secure REST API is the gatekeeper for the actual data.
That makes a lot of sense. Use the webhook for speed, use REST for robustness and security.
Okay, shifting gears slightly to performance, especially for REST APIs handling lots of traffic, two big optimizations come up constantly: caching and pagination. Let's start with caching.
Yeah, caching is absolutely essential for any API that needs to perform well under load. It's basically about storing copies of frequently requested data closer to the client, maybe in the browser, maybe at a CDN, maybe in an intermediary cache layer.
The goal being
To avoid hitting the origin server and doing the same expensive database query or computation over and over again, our sources even show graphs the difference in response time and throughput with and without caching is often dramatic, like order of magnitude improvements. But caching has that classic problem: stale data. How does a REST API tell the cache, hey, this data is old now, don't use it?
through HTTP headers. That's the contract. The server uses headers like cache control and expires in its response.
Cache control.
Yeah, cache control is really flexible. The server can say things like public, meaning any cache can store it, or private, only the end user's browser should cache it. It can set a max age in seconds. This data is fresh for 1 hour. Or it can say no cache, meaning the cache must check back with the server before using the stored copy, or even no store, meaning don't cache it at all.
So the API dictates the caching rules.
It has to. Otherwise, caches wouldn't know what's safe to reuse.
What about checking if the data has actually changed since the cache last saw it without re-downloading everything?
Oh, that's where e-tags come in. An e-tag or entity tag is like a version identifier or fingerprint for a specific version of a resource. The server sends it in the response setter. For example, e-tag xyz123. The client, or cache, stores that e-tag. The next time it wants to request the same resource, it includes that e-tag in an if-none-match request header.
Telling the server, only send me the data if it's different from version xyz123.
Exactly. If the data on the server hasn't changed, its e-tag is still xyz123, the server just replies with a very small 304 now not modified status code and an empty body. No data transfer needed. Saves a ton of bandwidth.
Very cool. Okay, the other big performance technique, pagination. You can't just return like a million search results in one go.
Definitely not. Pagination is just breaking up large sets of results, like a list of users, products, transactions, into smaller manageable chunks or pages. It's crucial for performance, reducing server load, and preventing timeouts.
But there are different ways to do pagination, aren't there? And some are better than others.
Yes, and this is important. The two main methods are offset pagination and cursor-based pagination.
Offset is the traditional one, right? Like page 2 and limit 50.
Yeah, that's offset or limit offset pagination. You tell the server, skip the first 50 records and give me the next 50. It's simple to understand and implement initially,
But
it performs poorly on large data sets. Especially in databases, asking for page 10,000 might require the database to scan and discard 499,950 rows first. And worse, it suffers from the data drift problem.
data drift.
Yeah, imagine you're looking at page 2. While you're looking, a new item gets inserted at the beginning of the list. When you ask for page 3, the items have all shifted down by 1, so you might see the last item from page 2 again, or miss an item entirely. It breaks consistency, especially with frequently changing data.
Ah, okay. I can see how that would be bad for like an infinite scrolling feed.
Yeah.
So what's the alternative? Cursor-based pagination.
Exactly. Cursor pagination, sometimes called keyset pagination, avoids the offset issue. Instead of page numbers, the API response includes a cursor, which is an opaque token pointing to the last item on the current page.
Opaque meaning the client doesn't need to understand what's inside it.
Right. It could be the item's ID or a timestamp or some combination. To get the next page, the client sends that cursor back to the server, essentially saying, give me the next 50 items after the item represented by this cursor.
And that solves the drift problem.
It does, because the query is anchored to a specific item, everything after item X, not a numeric offset. Doesn't matter if items get inserted or deleted before item X. It's also generally much faster for databases on large tables, as it can often use an index efficiently. It's the recommended approach for most modern APIs dealing with large collections or feeds.
Okay, we've talked design, performance, but none of that matters if the API isn't secure. Let's shift focus entirely to security, starting at the foundational layer.
Layer 1 has to be transport security. HTTPS using TLS, transport layer security. This is absolutely non-negotiable, period.
No excuses for plain HTTP anymore.
None. If you're not using HTTPS, everything API keys, passwords, session tokens, sensitive data is flying across the network in plain text. Anyone listening in the middle, a man-in-the-middle attacker, can just scoop it up. You must encrypt the channel.
Okay, HTTPS is the baseline. Moving up a layer, we get to identity and permissions. We need to be really clear on the difference between authentication and authorization.
Yes, critical distinction. Authentication is about verifying identity. Are you who you say you are? This is logging in, validating an API key, checking a JWT signature.
Proving you are you.
Right. Authorization, on the other hand, is about permissions. Okay, you are who you say you are, but are you allowed to do what you're trying to do? Can this authenticated user access this specific resource? Can they perform this delete operation?
So authentication gets you in the door. Authorization determines which rooms you can enter and what you can do inside.
Perfect analogy. And you absolutely need both enforced rigorously. A failure in authentication lets bad actors in. A failure in authorization lets legitimate users do bad things.
Let's talk about specific authentication schemes suitable for REST's stateless nature. JWTs and OAuth 2.0 come up a lot.
Right. JWT's JSON Web Tokens are really well suited for stateless APIs. As we touched on earlier, they're self-contained tokens.
Header, payload, signature.
Exactly. The payload carries claims, user ID, roles, expiration time. The signature, created with a secret key or a private key, guarantees the token hasn't been tampered with. The beauty is, the server can validate that signature without needing to check a central database or session store, preserving statelessness.
Makes them great for microservices too, right? One service issues the token, others can validate it independently if they have the public key.
Precisely. Very scalable. Now, OAuth 2.0 is a bit different. It's really an authorization framework, not just an authentication protocol.
Framework, how so?
It's designed primarily for delegated access. Think log in with Google, or allowing a third-party application to access your calendar or photos without you giving that app your actual Google password.
So it's about granting limited permission to another application on your behalf.
Exactly. OAuth uses access tokens that are typically short-lived and have specific scopes attached, defining exactly what the third-party app is allowed to do. For example, read profile, post tweet. It's the standard for securing third-party integrations, but managing those scopes and token lifecycles is crucial.
Okay. And what about simple API keys? Still see those around.
You do. API keys are simpler, just a unique string that identifies the calling application. They're often used for public APIs or internal service-to-service communication, but they're generally less secure than JWTs or OAuth. They often don't have built-in expiration, rotation can be manual, and they don't easily convey user context or fine-grained permissions. Use with caution, especially for sensitive operations.
Right. Okay, let's dive into the specific vulnerabilities that plague APIs. OWASP has their API security top 10 list. The number one is often broken object level authorization, or BOLA.
Yes, BOL is consistently at the top, and it's conceptually simple but devastating. It happens when an application doesn't properly verify that the user making the request is actually allowed to access the specific object or resource they're asking for.
Give us an example.
Imagine you're logged into your bank's mobile app. You make a request to see your transaction history for account ID 123. Get T AP accounts 123 transactions. Authentication checks out, you're logged in. Now, what if you, or an attacker, just manually change that ID in the request to get AP accounts 456 transactions?
Try to access someone else's account.
Exactly. If the API only checks, is this user logged in, authentication, but fails to check, does this logged in user actually own account 456, authorization at the object level, then boom, you get someone else's transaction history.
Wow. That's a horizontal privilege escalation, accessing data belonging to other users at the same privilege level.
Precisely. It boiled down to missing that critical check. It user authorized for object, user it objected. Every single time an object ID comes in a request.
Okay, related to that is broken function level authorization, or BFLA. How's that different?
BFLA is about vertical privilege escalation. It's not about accessing someone else's data, horizontal, but about accessing functionality you're not supposed to have access to, usually admin-level functions.
So a regular user accessing an admin endpoint.
Exactly. Maybe there's an endpoint like POST AP administrators used promote. A regular user discovers this endpoint, maybe through documentation or just guessing common paths. They try calling it for their own user ID.
And if the API checks they're logged in, authentication, but fails to check if their role is actually admin before allowing the promote function.
Then the regular user successfully promotes themselves to an administrator. Again, it's a failure to enforce permissions, but this time at the function or operation level, not the data object level.
Both BOLI and BFLA sound like fundamental authorization failures.
They are. They often stem from insecure defaults or developers forgetting to add the necessary checks consistently across all endpoints and methods.
Okay, another nasty one. Mass assignment. This one feels like it exploits convenience features in frameworks.
It totally does. Many modern web frameworks have features that automatically bind incoming data from a request, like a JSON payload, directly to internal objects or database models. It saves coding time.
So if I send email, new@email.com, address 123 mainsend to update my profile.
The framework might automatically map email to the user.email property and address to user.address. Super convenient.
But where's the vulnerability?
The vulnerability occurs if the attacker injects extra, unexpected properties into that JSON payload properties that exist in the internal user model but shouldn't be settable by the user. For example, they send email attacker@evil.com address is admin.
Trying to sneak in that is admin flag.
Exactly. If the API code blindly trusts the automatic binding and doesn't have an explicit allow list of fields that are permitted to be updated through this endpoint, the framework might just map is admin true directly onto the user object and save it to the database. Instant privilege escalation via data binding.
So the fix is strict input validation or using data transfer objects,
Yeah.
DTOs, that only expose the allowed fields.
Precisely. Never trust automatic binding with user-supplied data without explicitly defining what fields are allowed. Always use an allow list approach.
Okay, let's switch gears to securing webhooks specifically. We said the endpoint is public, which creates a different threat model. How do we ensure incoming webhook calls are legitimate?
The number one defense here, absolutely critical, is signature verification.
How does it work?
Since anyone on the internet could potentially send a POST request to your public webhook URL, you need a way to verify the request actually came from the legitimate provider, for example, Stripe, GitHub, your e-commerce platform, and hasn't been tampered with.
Okay.
The provider generates a cryptographic signature, usually using HMAC SHA-256. This involves taking the entire request payload body, combining it with a secret key, a password that only the provider and you, the client, share, and hashing the result.
Got it. Shared secret payload hash function.
Right. The provider then includes this generated signature in a special HTTP header with the request, XHub signature 256. When your webhook receiver gets the request, it performs the exact same calculation, takes the received payload body, uses its own copy of the shared secret, and computes the HMASC SHA-256 hash.
And then compares its calculated hash with the one sent in the header.
Exactly. If they match perfectly, two things. The request definitely came from the provider because only they have the secret key, and the payload hasn't been altered in transit because any change would result in a different hash. If the signatures don't match, you reject the request immediately. It's fake or corrupted.
Signature verification handles authenticity and integrity. But what about replay attacks? Someone captures a valid, signed webhook request and just sends it again later.
Yeah, that's a real threat. Imagine capturing a payment received for a $100 webhook and replaying it 5 times. Not good.
How do we stop that?
2 main techniques. First, include a timestamp in the webhook payload. Your receiver should check this timestamp and reject any request that's older than a short tolerance window, maybe 2 to 5 minutes. This drastically shrinks the window of opportunity for a replay attack.
Makes sense. What's the second technique?
The second, and arguably more robust approach, especially because webhook providers often guarantee at least once delivery, meaning duplicates can happen naturally, is to design your webhook processing logic to be idempotent.
Idempotent again, meaning processing the same request multiple times has the same result as processing it once.
Exactly. For that payment received webhook, your handler logic must first check. Have I already processed payment ID XYZ from this provider? If yes, it should just acknowledge the request with a success status but do nothing further. If no, then it processes the payment.
So idempotency handles both malicious replays and legitimate network retries from the provider.
Correct. It makes your system resilient to duplicates from any source. It's a crucial design principle for reliable webhook handling.
And one last point on webhooks and data.
Right. Best practice. Don't send highly sensitive data, PII, credentials, directly in webhook payloads if you can avoid it. Use webhooks for the notification, the signal, and then use a secure, authenticated REST API call to fetch the sensitive details if needed. Keep the webhook payload lean and focused on the event itself.
Theory is one thing, but seeing how these vulnerabilities play out in the real world, that really drives the point home. These big breaches often come down to missing the basics we've just discussed. Let's look at British Airways in 2018. What went wrong there?
Oh, BA was a cascade of failures. It apparently started with a compromised account at a third-party supplier, an account that crucially lacked multi-factor authentication, MFA. That got the attackers a foothold.
Just basic MFA could have stopped it at stage 1.
Potentially, yes. Once inside, things got worse. Reports suggest they found things like an administrator password stored in plain text within a script file, just sitting there.
Wow. Okay, so credential hygiene failure. Where did the API or web vulnerability come in?
It seems they exploited weaknesses in how BA handled payment processing on their website and possibly mobile app. They managed to inject malicious JavaScript code, a skimming script, into the payment pages. This code was likely loaded via a compromised or outdated third-party script that BA was using.
So as users typed in their credit card details,
The malicious script grabbed the card number, expiry date, and the CVV code from the form fields and sent it all off to the attacker's server before the legitimate payment process even completed. They also apparently found a testing feature left active in production that was logging excessive payment details, potentially including CVVs, making things even easier.
Leaving test code in prod. Another classic mistake. The result was a massive data breach and a huge fine, right?
Yeah, initially 183 million, later reduced to 20 million after appeals, but still massive. Huge reputational damage, too. It highlighted failures in MFA, credential management, third-party script security, and proper environment separation.
Okay, next case. Optus in Australia, 2022. You mentioned this earlier as a stark BLA example.
It was almost unbelievably simple, technically. Optus had an API endpoint that was publicly accessible, apparently intended for internal testing or integration, but it was left exposed to the internet.
Exposed and?
Exposed and required zero authentication. None at all. Anyone could hit it.
Okay, that's bad enough.
But the killer vulnerability was that this API endpoint allowed querying customer details using identifiers, and these identifiers were apparently sequential or easily guessable, like customer ID 1, customer ID 2, customer ID 3.
Oh no, so the attacker just wrote a script to loop through numbers.
Seems that way. They could just iterate GET APA customer details 1, GET APA customer details 2, GET APA customer details 3, and pull down millions of customer records, including names, dates of birth, phone numbers, addresses, even passport and driver's license numbers in some cases.
Just wide open BLA on an unauthenticated endpoint using innumerable IDs. That's textbook failure.
It really is. A catastrophic failure of basic API security fundamentals, authentication, and authorization led to one of Australia's largest ever PII breaches.
Unbelievable. Let's move to T-Mobile. They've had multiple incidents, but let's focus on the one spanning late 2022 into early 2023. 37 million customers affected.
Yeah, T-Mobile has unfortunately had a rough run. In this specific incident, the attacker exploited a single vulnerable API. The exact flaw wasn't publicly detailed by T-Mobile, but security researchers widely suspect it was either another BOLA variant or perhaps a broken authentication mechanism on that specific API.
And the attacker used this one API
to systematically exfiltrate customer data over a period of more than a month, from late November 2022 to early January 2023. They pulled names, billing addresses, emails, phone numbers, dates of birth, T-Mobile account numbers, a huge data set.
Over a month. That points to another failure, doesn't it? Monitoring and detection.
Absolutely. The technical vulnerability, BOA or similar, was the entry point, but the fact that an attacker could continuously siphon off data from a single API for 30-plus days without triggering alarms suggests a significant failure in security monitoring, anomaly detection, and behavioral analytics. That volume of data exfiltration from one source should have raised red flags much sooner.
Right. You need to detect unusual activity patterns, not just prevent the initial exploit.
Okay.
One more recent case. Dropbox Sign in 2024. This one highlights the supply chain risk.
Yes, the Dropbox Sign, formerly HelloSign incident, is really interesting because it wasn't necessarily a flaw in their own core application code, but rather a compromise of their infrastructure and associated credentials.
How did it happen?
Reports indicate attackers gained unauthorized access to Dropbox Sign's production environment. They managed to compromise a service account used for back-end systems, and from there they were able to access customer information.
Okay.
But critically, they also got hold of authentication secrets used by Dropbox Sign. This included things like API keys, hashed passwords, and crucially, OS tokens that customers had granted Dropbox Sign to integrate with other services like Google Drive, Salesforce, etc.
So the attackers stole the keys that let Dropbox Sign talk to other apps on behalf of users?
Exactly. This created a potential ripple effect. If attackers got the OAuth tokens, they could potentially impersonate Dropbox Sign and perform actions within those integrated third-party platforms, leveraging the permissions users had already granted.
That's terrifying. It means your security isn't just about your own systems, but also about how securely your vendors handle the permissions you delegate to them.
Precisely. It underscores that your attack surface extends to every single third-party integration that relies on delegated authentication, like OAuth. The supply chain is part of your security perimeter now. #8. Conclusion and final thought.
Wow. Okay, we've gone from the architectural elegance of REST and the event-driven nature of webhooks right through to the devastating consequences when these things aren't secured properly.
Yeah.
If you're listening to this, maybe you're an architect, a developer, a security professional. What's the single biggest imperative here? The core message?
I think the core conclusion, tying everything together, is that building reliable, scalable, and secure digital systems absolutely depends on rigorous adherence to these established best practices. It's not optional.
Things like,
True statelessness in your REST APIs, logical resource modeling, predictable use of HTTP methods, and then the security fundamentals. HTTPS everywhere, strong authentication and authorization on every single request, proper signature validation for webhooks, designing for idempotency. These aren't nice to haves, they're foundational.
and critically, as the case studies showed, the big headline-grabbing breaches are rarely super sophisticated zero-day magic. They're almost always failures to implement these known basic controls.
Exactly. It's often about missing the fundamentals. Security needs to be baked in from the start. Security by design isn't just a buzzword, it's essential practice.
So let's give our listeners a couple of really concrete, actionable takeaways. Where should they focus their attention right now?
Okay, two key areas come to mind based on our sources and the incident patterns. First, continuous API discovery and inventory. You cannot secure what you don't know exists.
The shadow API problem.
Right. APIs pop up everywhere now, developed by different teams, maybe without central oversight. And then there are zombie APIs, old versions or forgotten internal APIs still running. Organizations need automated tools and processes to constantly discover and inventory every API they expose, internal or external. The attack surface is always changing.
Know thyself, know thy APIs.
Yeah.
Okay, what's the second focus area?
Second, double down on strict access controls and input validation. This directly addresses the biggest threats we discuss.
BOL, BFLA, mass assignment.
Exactly. Implement fine-grained authorization checks, verify object ownership for BOA, and required roles permissions for BFLA on every sensitive endpoint and operation. And be ruthless about input validation, especially for updates. Use explicit allow lists for fields that can be modified via an API to prevent mass assignment. Don't trust incoming data.
Makes sense. Discover everything, lock down access, validate input. Okay, that brings us to our final thought for you, the listener. Just maybe ponder after this deep dive.
Yeah, thinking about the increasing interconnectedness, especially highlighted by incidents like Dropbox sign or the earlier Moviate transfer vulnerability, it really shifts the security landscape.
How so?
Your organization's actual security posture, your real-world risk, is becoming less defined just by the systems you directly build and control, and more defined by the security practices of your entire digital supply chain and the rigor with which you manage delegated access.
So it's not just about your API security, but the security of every third-party service you integrate with via their APIs, especially when using things like OIF.
Precisely. How well do you audit the permissions you grant via OIF? How quickly can you revoke tokens if a provider is compromised? How closely do you monitor the activity tied to those delegated credentials? That ability to manage and monitor the security of your external dependencies and integrations, that feels like the next major battleground for enterprise security. Your trust in others is now a core part of your own risk profile.
That is a really critical point to consider. The perimeter isn't where it used to be. Well, thank you so much for breaking all this down for us today. It's clear just how vital getting REST and webhook design and security right truly is.
Absolutely essential in today's world. My pleasure.
We'll see you next time on The Deep Dive.